Hello everyone. Today we are going to be talking about the Cantor set. We're going to do a little bit of measure theory, just because I feel like it. We're going to be talking about about the Cantor set, specifically the Cantor set in relation to the Lebesgue measure on the real numbers. Okay, so the Cantor set is is a the most well-known example for an uncountable set of measure zero. So it's uncountable with uh, measure zero, and of course I'm talking about the Lebesgue measure here. Okay, so I'm gonna be writing M for uh, the Lebesgue. This is a G. The Lebesgue measure. Okay. And let's define this set. So we start off with the unit interval, the closed unit interval. Okay, I'm gonna draw that over here. So this is gonna be E0. And now I'm gonna define a function, call it alpha, from the power set of the real numbers, so all the subsets of the real numbers, to again the power set of the real numbers. So it takes in a subset of the real numbers and spits out a subset of the real numbers. And we're going to define it in the following way. So alpha s is going to be third s union one third s plus two thirds. And now I'm going to define what I mean by this. So take alpha to be a real number. And yes, let beta be a real number as well. So alpha s, where s is a subset of the reals, is going to be equal to alpha s, well, where small s isn't big S, and uh, s plus b is going to be defined in the same manner. S plus b, where s small s is an element of big S. Okay, uh, and let's just look at what uh, alpha does to E0. So it shrinks it by a third. Okay, so then that's going to be 0 to 1/3, and it unions that with shrinks it by a third and adds 2/3. So this is going to be 2/3 up to 1. So this is going to be uh, alpha of E0. So what we've basically just done is we've removed the middle third from E0. Okay, and we're going to call this E1. And in general, we're going to define En to be alpha, the composition of the function alpha n times, and with E0 as its uh, as its the element it acts on. Okay, so basically what we do at every step for E2, we just we just delete the middle third out of every closed interval we have. So we create two new closed intervals, but without the middle third. And we continue in this manner. So this would be E3 and so on. And the Cantor set is basically going to be the limit of this process. And we know what a limit is when talking about sequences, about functions, but you can't really write down uh, this. This really doesn't make sense in the set theoretical world because these are sets. It's not really defined. So how do we get around that? Well, we define the Cantor set, call it C, to be the infinite intersection of all the EIs. And for this to work, for us to be able to take this limiting process, the sets have to be nested. The sets have to be nested. Okay, so the Cantor set is this weird limit set, the infinite intersection of these sets where we just remove the middle third and we go on, and they're nested, so we're gonna be left with something. And now the two things we want to show is that the Cantor set has Lebesgue measure 0 and uh, that it's uncountable. Okay. Uh, and first we are going to show that the Cantor set has measure 0, and this is a claim. Okay. Uh, Now we're just gonna have a look. We're gonna have a look at what mm, we're gonna have a look at what alpha does to a measure of a set uh, a n minus one. Okay, so this is going to be en, uh, and this is going to be 1/3 of en minus one union 1/3 of en minus one plus 2/3. Okay. This is a 3. And now we ask ourselves what the measure of this guy is. What the measure of this guy is. And that's going to be the measure of this. Union this. Okay, we copy that down. And one can quite easily see that these two sets are disjoint because we've shrunk down en minus 1 to by 1/3, and then we've translated this guy with 2/3. So these guys are going to be disjoint because you have a set, you shrink it down to a third, and then you translate it by 2/3, you're going to get this. So we have that these two sets are going to be disjoint, meaning that we can simply do this by subadditivity, by additivity. Okay. Uh, what does translation do? What does translation do to the measure of a set? It does absolutely nothing. It just moves it about. So we can basically just cross this and just look at this. So 2 times the measure of this. And this is just, well, it's just this set shrunk down by a third. So what happens when you shrink down a closed set by a third? Well, its measure just shrinks down to a third. This, in fact, works for all Lebesgue measurable sets, but it obviously works for unions. So En is a union of closed sets. Because when we while we're constructing the Cantor set, you can see that at each step we just take out the middle third and we're left with uh, disjoint closed sets, unions of them. So, and when we have a closed set, when we just shrink it down by a third, well, its measure just shrinks down by a third as well. So this is going to be 2/3 of the measure of En minus 1. Okay. And what is En minus 1? Well, that's going to be just alpha of En minus 2. And we have a recipe for this, so we're fine. So this is going to be 2/3 times 2/3 times the measure of En minus 2. Okay, and uh, we continue in this way, and once we get to E0, the measure of E0 is going to be 1, and thus we have that this is the case, that the measure of En is going to be 2/3 to the power of n. Okay, and the Cantor set, as these sets are nested and as this is the intersection of all the En's, is going to be a subset of En, in particular for all n. Okay, for all n. In particular, that's going to mean that the measure, and this is due to subadditivity, that the measure of the Cantor set is less than the measure of En, which is, as we've calculated now, 2/3 to the n. And this holds for all n. And now, taking the limit of n, taking n to infinity, gives us that the measure of the Cantor set is 0, 0. Okay, so this guy, this limit of just a sprinkling of points, is going to have measure 0. Okay, and now all that is left to do is show that this set is uncountable. Now I'm gonna write a claim. Uh, an element of 0, 1, such that a real number between 0 and 1, such that when A is written in ternary expansion, so in base 3, if di is 0 or 2 for all I, okay, I'm going to remove this if. So the claim is di is 0 or 2 for all I if and only if A is an element of the Cantor set. Okay, and we only need to show this direction. We only need to show this direction. So if all the di's are either 0 or 2, then the real number is going to be an element of the Cantor set. We only need to show this direction in order. Both directions are true, but we only need to show this one in order to show that the set is uncountable. So I'm just gonna write down an example. I'm not gonna do a whole proof, but I'm going to show you why this works, and you can easily construct the proof on your own. So I'm gonna just write down a number in ternary expansion which has all zeros and twos, has no ones basically. Okay. So what does this mean? This means, uh, well, this is equal to, if we expand it in base 10, uh, 0 times 1/3 plus 2/9 plus 2/27 plus 0 81s and so on. Okay, so this number is obviously between 0 and 1. Okay, so this number is an element of E0. And look what happens every time we pick a digit. We pick the next digit, it being 0 or 2. If we pick 0, if we pick 0 as the first digit, that means that our number cannot be possibly bigger than this, than 1/3. It cannot possibly be bigger than 1/3. Uh, so our number is going to be an element of this set 0 to 1/3. Okay. Then when we look at what happens when you pick the next digit, okay, 2. So 2/9. So this says, if you calculate, so that's 1/3, so that's 0 plus 2/9. So this is a ninth. So that means our number is uh, not smaller than this and cannot possibly be bigger than this. So our number is an element of this guy. And then again 2, this means that further by the same logic that our number is an element of this guy. And then we pick a 0, our number is an element of this guy. And we go so on, and always as we pick the next digit, we're just basically deciding whether uh, whether the whether our number is an element of the left third or the right third. And so in this way, one can show very easily inductively that our element is going to be, so let's say this was A. A is going to be an element of En for all n, implying that A is an element of the Cantor set. Okay, and what does that mean? Every number of this form where the digits are either 0 or 2, so there's no uh, um, digit 1, is going to be in the Cantor set. So that's good. That's good. And simply by Cantor's diagonal argument, the same way you do for to show that the reals are uncountable, you can do the same thing here. You can do the exact same thing here. Uh, and this basically shows that C is uncountable. And the Lebesgue measure of the Cantor set is 0. So isn't that wonderful? We found a set that is uncountable with measure 0. So it's a funny set. Well, it's rather nice actually. And not only is it uncountable, it in fact it has the same cardinality as the set 0, 1. Now I know this may seem strange, but one can easily construct a surjective function from the Cantor set to 0 and 1. And how does one do that? Well, you just you take a number which has all the digits zeros or twos, okay, and then you just replace all the twos with ones, okay. So this is written in ternary, and this, once you replace all the twos with ones, you can just look at this number as a number written in the in binary uh, uh, in binary in base 2 in binary expansion. And every number between 0 and 1 can be written down in base 2. Hence, you can find for every number written down in base 2, you can find the um, the appropriate number written down in base 3 with zeros and twos. So that's how you do it. So and since the Cantor set is a subset of 0, 1, it can't have a bigger cardinality than 0, 1. So C has the same cardinality as 0 and 1, and these are obviously infinite cardinalities, so I won't I won't get into it that much, but they do have the same cardinality. Okay, thank you everybody for watching, and I'll see you next time.